Okay, thanks for sticking with us. Here we are with our honors stats students to talk about a sampling distribution model for a sample proportion. So we have this scenario where we have all the cars on the interstate. We were saying that 80% exceed the speed limit. All right, that's quite high. What proportion in Texas? What proportion of speeders might we see among the next 50 cars out on some highway? Okay? Before you do anything, all right, you always want to think the very first thing is to make assumptions. Okay? So we're going to write down the first assumption, which is the independence assumption. All right, I'm going to type out the sentence that I would write, but who wants to give it a try? Who wants to give it a try for what they would write to assume independence for this problem? Who wants to give it a shot? Anyone? No one. Say it, Jarvis. Ah, Jarvis. No? The values. What's the value you're talking about? Well, those are different, right? The 50 is just the number of cars, Leslie. I can make that 50 into 100. It doesn't matter the sample size, right? Really just think about what are we looking at here, Leslie? The speed of the cars, right? So if I look at a car zoom by, okay, and then I look at the next car that zooms by, do you think that those are independent speeds? He's nodding yes. Okay, so we're going to write that one. Wow, that's not where I want to do that. Can I do it here? Can I do it in there? Let's see. Yes. One car's speed does not affect another car's speed. Now, I said the answer. We're in a class that there's not really an answer, Jarvis, so it doesn't really apply here. Sorry, man. This is the statement I would write. Whether you agree or disagree, you want to get into the habit of writing this kind of statement, that one event happening does not affect the next one. Now, does anyone disagree with this statement? So, why do you disagree?
Because there's like a group of cars speeding, you might have a less chance of being singled out by a cop.
So you're saying that if you see a car speeding, you think that if there's a bunch of cars back to back to back to back, that maybe they're all speeding. Okay, interesting. Now you mentioned something about being pulled over by a cop. Can you think of another scenario where maybe they're all not speeding? Okay, so we're talking about like there was an accident, and it could be like rubbernecking on the other side of the road they're looking. I was thinking like whenever you see a cop that's just sitting, everyone's like, everyone slows down a bit, right? So there are scenarios where you guys just came up with that they probably would not be independent events, okay? But what conditions, we are assuming, David, what conditions can we check? Very good, let's start there. The randomization condition. Okay, now the randomization condition, you're looking for anything in the problem that states they randomly sampled. Well, how did they get these 50 car speeds? They just chose the next 50. Is that random? No, that's not random at all. So what you're going to write, this is this like the weasel words you're going to write, these 50 cars are a good representation, spell representation, right, of all cars. That's not what I wanted to do. Go back. Thank you. Try again. There we go. Nope. I'm going to get it. I do that before. Well, I'm just going to leave it. Clearly, it doesn't want me to do it. Okay? So if you're ever looking at a problem and it doesn't say anything about randomization, then this is the go-to sentence you want to write. That this sample is a good representation of the population. Okay, what's the other condition? underneath independence assumption. Very good, Leslie. The 10% condition. Now, I actually do a little bit of math here. Okay? What is the sample size?
50.
It's 50. So n is 50. All right. Then I take n, that's 50, and I multiply it by 10. So what is 50 times 10? 500. So let's think about this. We're thinking about like the greater Houston area. Are there more than 500 cars on whatever highway we're looking at?
Yeah.
Most likely, yes, right? So basically by doing this, we feel confident by saying that we can say that 50 cars is less than 10% of all cars. Okay? So we're trying to make sure in the 10% condition that the 50 number is not too big. Okay, so it's not too big. Okay, who's got questions on what we've done so far? No questions? Okay, let's move. Yes, question. Charlie. So we're not there yet. All we've done so far is the independence assumption and check the conditions for that, which is randomization and 10%. Now we've got to do the other assumption, Charlize, which is the sample size assumption. It's okay however you order it. If you've run out of room, just go underneath it. Okay? So what statement am I going to write for these? That's a condition. I need to write a statement. Whenever I make an assumption, Wences, you want to write something first. So I'm going to write 50 cars. Not good enough, close. You're really close, Travis. Is a large enough sample. Right? Because the sample size assumption is assuming that your sample is big enough. Okay? Now we are going to check, I heard Wences say it, we are going to check the success failure condition. Okay, so this is also going to require some math. N times P and N times Q. What is the probability that a car is speeding on the interstate? 80%. So that's 50 cars times 80%. And then 50 cars times that they're not speeding, which is 20% or 0.2. So what's 50 times 0.8? What's 80% of 50? 40, very good. And so then what is 20% of 50? 10. Are those numbers 10 or more? Yes. So you're going to write down both numbers are 10 or more. Oh. All right. Both numbers. Come on. Try again. No. I guess I'm going to use my pen. Both numbers are 10 or more. So 50 is large enough. Okay. So all we've done so far is we have written down the assumptions we're making and checked the necessary conditions. We haven't done any math. Yeah, we did a little bit. But we haven't really done any stats yet. We're just basically laying the foundation for being able to do it. Who's got questions on the assumptions and conditions part? And again, you're going to have to memorize how to do all this. You got lots of time, not until next Wednesday. Okay, so let's actually make the model. All right? We're ready to make it. I'm going to write down, we have a normal model, and going from the notes, we're going to use P as the mean, and the standard deviation is going to be the square root of P times Q over N. So if you have a yellow calculator, this will be helpful. So for this model, we all know that our proportion of these cars that are speeding is 0.8. And to find our standard deviation, let's go ahead and plug in some numbers here. So we have 0.8 times 0.2 over 50. All right? So if you have a calculator, you can type this in. Jeez Louise, Wences. All right? You can type it in. 0.8 times 0.2 divided by 50. And take the square root of that. And I got 0.057. Oh, no, like this 0.8? No, it's separate. It's like we need a second number. You're good. And then we'll confirm for me 0.057. Yes, excellent. 0. Okay, so once you have your normal model and your parameters, that's what these are called again, this mean and standard deviation are called the parameters, you're going to draw your curve. Okay, so do your best curve. Something like that. Thanks, Bianca. Practiced a lot over the break. All right, right down the middle. Right down the middle is going to be the mean. All right, which is 0.8. And then I'm going to go 1, 2, 3 standard deviations above, and 1, 2, 3 standard deviations below. All right, so take your calculator and do 0.8 plus 0.057 3 times. All right, so I've gone all the way to 3 standard deviations above. Now I'm going to go the other way with subtraction. Very good, Jarvis. So 0.8 minus 0.057. Okay. Now, once you get to this point in the process, I know many of you are catching up, so I'll slow down a little bit. The hardest part, I think, for students that are learning this for the first time is not necessarily learning how to get the numbers, because you guys will practice enough, you're strong mathematics students, you'll be able to figure out how to get all these numbers pretty quickly. It's what do they mean? That's the hardest thing to understand, okay? So you're going to get your wrists ready. We're going to do a lot of writing here. All right, so find a spot. I left a little room below. Hopefully you left a little room below. If you haven't, then, okay, you don't need to write. But I want to write down what all this means and try to explain the best I can what this means if we were to actually think about going on a highway and finding the speeds of cars, which we're not going to do because that is dangerous. All right, here we go. You let me type? Let me type, please. The numbers went away, but I'll type anyway. Okay, so according to the normal model, that's not good. Caps lock. I'm trying to write a comma. That's a comma. We expect 68%. I won't let me do numbers either. Give me a second. That's 68. It is, I swear, I'm typing 68. Let me try it. Nope, it doesn't like that. Yes. Yeah, I tried doing that. That's fine. I'll just write 68. I'm really struggling here. Oh, now you would let me do it. We expect 68% of the samples of 50 cars, I'll go back, put the numbers, to have proportions of speeders between, and then I'll put our first numbers, 95% of the samples of 50 cars to have proportions between the next two. And 99.7% of the samples of 50 cars to have proportions between the last two. Okay. I'm putting the numbers in right now. I got you. Let me try. Okay. So this was 68%. Oh, I got two 68s now. Okay. So when I say the 68%, do you guys remember from last semester the 68, 95, 99.7 rule? That's where those numbers are coming from. So if you look at what you wrote down in your model, go one standard deviation above and one standard deviation below, and you should see the numbers 0.743 and 0.857. You guys see those two numbers? Okay? So it's just like continuing with that same idea. And this one is going to be 95% of them. You're good. So now I'm going another standard deviation, going to the next two. So 95% of those samples will have proportions between 0.686 and 0.914. And then 99.7%. Oh, I guess I got room there. I left room. That's room. There we go. And the last one is 0.629 and 0.971. Okay, so let me try my best, since that was not great, to explain to you what I mean here. So we're not actually going to do this, right? We're not going to get a radar gun. We're not going to go on the freeway and seriously, we're not going to do that, right? That's huge liability issues, okay? But I want everyone to imagine that you're about to do that, right? It's about to be rush hour. So imagine whatever freeway you want, 45, 288, 59, I-10, whatever you want, that you're going onto a freeway with your radar gun, okay? You're looking at the next 50 cars and you're writing down all of their speeds. Okay, and then you're calculating how many of those 50 are speeding. Okay, so let's say Saul does this. Okay, Saul does this, and Saul, what percentage of your cars were speeding? What percentage of your 50 cars were speeding? 80%. Okay, so his was 80%, which is, coincidentally, exactly the proportion we expected. So if he comes back with 80%, would I be that shocked? No. All right? Let's go with someone else. Laura, what about you? Your sample of 50 cars. What was your percentage that were speeding? 75%. Now, 75% is almost one standard deviation away from the mean. Is that unusual to be almost one standard deviation? No, it's not that unusual. So Laura's number, not that unusual. Okay, Bianca, what about your number? 24%. So she only found 24% of her 50 cars were speeding. But if you look at your curve, what's the lowest number that we're expecting? Something around 63%. So if Bianca comes back and tells me that 24% of her cars are speeding, then I'm saying what? Whoa, that's unusual. All right? And so then maybe I ask her, Bianca, where were you? You were at 610. Was there something interesting going on while you were looking at those cars? There was a crash. All right? There was a wreck. And that could explain the number. All right? Thanks for playing along, Bianca. That was so great. You're the best. Okay? So that's all these models are saying with your curves, is that you're expecting, if you were to go do it, that you would expect to be in between those numbers. And if you're not, doesn't mean you're wrong. It just means that something unusual has happened. Something odd is going on. Exactly. You want to just figure out what happened. Okay? Okay.